chapter 14. So first of all, let me write for the videotape. This is chapter 14, and it's called Multiple Regression, as compared to chapter 13, which was simple regression, where if you recall in chapter 13, the formula we've been using b0 plus b1 times x. And now simply, but if you recall also, because this is what this first slide is all about, the underlying model, which I didn't spend too much time because it's a little theoretical, the underlying model that says how do you relate the x to the y, you know, in terms of the scattergram, that the typical y value can be figured out based on knowing the intercept of the equation and the slope relating an x to a y, but because this represents a perfectly straight line, and the reality is that dots are a little bit off the straight line or a lot off the straight line, we have to add on a term into the model to indicate that we recognize that reality and deal with that mathematically. So this is the equation that we're dealing with in chapter 13, and of course the y hat is an estimate of the y. I mean, we're not really, the y hat is the straight line, but the b0 is an estimate of the beta 0, the b1 is an estimate of the beta 1. And to point out to you in chapter 14 is basically an extension of that. Instead of having simply one variable predicting a y variable, now we have many variables predicting a y variable. This is unnecessarily complicated, so let me put it down in my slightly more simplified form. Let's take an example where you have two variables. You have y equals, let's take a concrete example. You want to try to predict somebody's weight based on their height, which is the x. But now we have, in addition to height, we also have, let's say, somebody's age. Age also affects, so that's another independent variable, somebody's age. We'll call this the x1, we'll call this the x2, and the equation now becomes, this is going to be in terms of predicting the straight line, b0, it's still going to be an intercept, b1 times x1. In other words, what impact does somebody's age have on their height? Plus, there's an impact of somebody's weight. I'm sorry, somebody's height on their weight. I'm sorry, let's try it again. B2 times x2. So this is what this equation is. So basically, we're taking the equation and extending it to another variable. And if you have a third variable, which you can sometimes have, b3x3 or b4x4, and once we have more than two x's, we can also talk about the combination of x1 and x2 together, which is what they said extra credit topic I'll talk about a couple of days from now. But right now we're just dealing with the simple additive model of simply adding together these separate terms. And we're not expecting the x1 and the x2 to have an interaction or a combination effect. That's going to be again the extra credit topic. So the question is, how do you calculate the b0, the b1, and the b2? And the answer is you don't have to calculate it. You simply produce the printout that I asked you to bring to class today, and then you get the numbers off the sheet, very similar to chapter 13. So what this is now. Before I want to point out to you that remember in chapter 13 we were able to make a picture. You plot x and y. You plot the straight line. How can you plot this? And the answer is, to save time, I'll answer my own questions probably today. The answer is you can't plot it really, because if you have x1, let's say in this direction, x2, so x1 equals 13, x2 equals 75, and that's a point right over here, right, where they meet. So where do you put the y? Well, the answer to y comes out of the board. So if you want to make a three-dimensional, like a Tinker Toy model, or somehow use some kind of a special effects to make it look like a shadow or whatever, which the book does do, maybe we'll see an example here. You can do it in 3 dimensions. What if you have an x3, a b3, x3? How can you, then you have 4 dimensions. You have the x3 x's and 1 y, which is a 4th dimension. Can you imagine making a picture in 4 or higher dimensions? The answer is no. So you really can't make a picture for these things. All you can do is sort of do the mathematics without really visualizing, which is why chapter 13 is so important, because you can visualize chapter 13. So let's get back into the simple case of just 2 variables. So your job is basically to do the following. So you have a certain number of objectives. First of all, to write down the equation. And this is simply write this equation by basically filling in the b0, the b1, and the b2 from looking at the proper part of the printout. The second objective of the chapter will be to make a forecast. In other words, I'll tell you, make believe x1 is equal to 13 and x2 is equal to 10. just simply multiply them and add them, and you're going to get the answer in 3 seconds. So that's making a forecast. Now, of course, if you want to get a little more sophisticated, you can create a 95% prediction interval for that forecast. We're not going to get into that. We did that in chapter 13, plus or minus the t-value and everything else. We're not going to get into that, but that's that. Objective number 3, which starts getting a little more sophisticated. Is the overall model useful? Remember how we did it? Is the model, meaning all these variables, meaning is x1 and x2 taken as a group, really forecasting the y value accurately? Which means the model, this equation that we claimed it was basically the underlying mathematical model, is the model useful? In other words, is this really a true representation of what's going on in our set of data? And if the answer is yes, then that's nice to know, and then we can use that information to make forecasts and all kinds of other stuff. But the first question we have to answer, or one question we have to answer, is the model useful? Now, just jumping ahead a couple of minutes, what would that boil down to? If the model is useful, if the model is not useful, what would this equation look like? Would there be any x's in the equation predicting the y? The answer is no, because it means that if the model is not useful, there's no x's. So how can you mathematically represent the fact that there are no x's? If all the betas, if beta 1 is equal to 0, 0 times anything means gets rid of the x1. If beta 2 equals 0, it gets rid of the x2. So the mathematical representation to answer this third question by hypothesis testing will be to start out by saying H0, beta 1 equals beta 2 equals 0, meaning they're all 0. That will be well, jumping ahead a little bit. The fourth objective is to answer, so assuming the answer to this question is yes, that the model is useful. Now, to the next question one might want to answer is, what about the x1 by itself? Is x1 really making a contribution to the equation? Is x2 making a contribution? Of course, it's possible. Let's say, for example, you're trying to predict somebody's weight based on knowing their height, their age, their sex. You can also have a variable of 1 and 2, or 0 or 1. Another variable could be, let's say, how much exercise they do, and a whole bunch of other variables. So let's say it turns out all those variables thrown into an equation like this actually do in fact make a pretty nice forecast of somebody's weight. The next follow-up question, in fact, I think the last part of the chapter will be, does age by itself really contribute to that equation? Right? What if you dropped out age? What if you dropped it out? Would the equation still be basically the same? So if the answer is yes, why throw another variable into the equation that's going to complicate things when the equation does almost the same job by dropping that equation? So the next thing does each xi, because xi means x1, x2, x3, make a contribution. Make a contribution to the model. And that will also be a hypothesis testing, because the answer will be yes or no. H0 will be what? Beta 1 equals 0, meaning that the x1 drops out of the equation. So we're going to get into that in a minute. So those are the 4 things we've got to do.